My name is Eugene Kennedy and I'm Science Secretary for the Royal Irish Academy. I'm here today in Trinity College where the Hamilton Lecture, the annual Hamilton Lecture, is about to take place in the Burke Theatre.
I suppose I'm chairman of the Arab Trust, and Arab are delighted to be associated with the Hamilton Lecture. We particularly think that in the current climate in Ireland, now is the time to be supporting events like the Hamilton Lecture to encourage people to do maths, and hopefully for us engineering then as a follow-on.
A very distinguished visitor this year, Professor Cedric Villani from Paris. Now, he was a Fields medalist in 2010. That's the equivalent of the Nobel Prize for mathematics.
I think somebody described him to me as the Lady Gaga of mathematics. So I think I'd much prefer to be here tonight than at a Lady Gaga concert.
My name is Eugene Kennedy and as Science Secretary it's my privilege to welcome you here this evening. Very welcome, Your Excellency, and everybody here in the audience. This is the annual Hamilton Lecture, which is run by the Royal Irish Academy every year since 2002. And it's brought to you in association with the Irish Times and the engineering firm Arab. On behalf of the Academy, I'd like to extend our particular gratitude to Arab for sponsoring the lecture this year, in particular to thank Claire Curtis, Jerry Mehigan and Fergus Monaghan. Arab are an independent global firm of designers, planners and engineers established as far back as 1946. And I'd like to especially welcome Jerry Keegan, Chair of the Arab Trust. Hamilton Day, as you can see by the numbers here, is one of the Academy's biggest outreach events. And with the support of Arab, we've been able to provide a day-long programme of events that engages students of mathematics, physics and engineering and recognises some of Ireland's top mathematics students. Earlier in the afternoon in the Academy buildings we presented awards to 9 of the top mathematics students all over the island of Ireland. This lecture celebrates, it's the 16th of October, so the date back is October the 16th in 1843, 171 years ago today, when many of you know the story when William Rowan Hamilton discovered quaternions. Now, he was president of the Royal Irish Academy at the time and he worked in Dunsink, and he was actually walking into Academy buildings to have a meeting, and no doubt he had been working on these conceptual problems for quite some time, but the inspirational spark happened when he was passing Broome Bridge, which is on the Royal Canal. And as I said earlier today, in an act of creative graffiti, he scratched the original equations on the bridge. I presume just in case they slipped his mind. But if you go there today, you'll see a plaque in honour of that particular event. And in fact, we've heard some very nice news today. Many of you recognise internationally Ireland is known for its writers, its poets, but maybe not so much for its science and engineers. And in fact, that should not be the case. In fact, Hamilton at his time was a world-renowned figure. In fact, he was the first foreign member of the US Academy of Sciences. But today the Minister for Transport announced that there'll be a Lewis stop near the Broome Bridge and there'll be a Lewis depot, and it will be named the Hamilton Depot. So gradually he's been recognised in his own. Now, our speaker this evening is Professor Cedric Villani, 2010 Fields medalist. He's professor in Lyon University and a director of the Henri Poincaré Institute in Paris. He was one of the 4 Fields medalists in 2010, and many of you will know this is the preeminent award internationally for performance, for achievement in mathematics. Professor Villani worked on the theory of partial differential equations involved in statistical mechanics, especially the Boltzmann equation, and no doubt we'll hear something about that today, and where he was the first to prove how fast convergence occurred for initial values not near equilibrium. And he also proved some outstanding theorems in relation to Landau damping, which has a lot of relevance for plasma physics. He is, in addition to the Fields Medal, he has won many international awards. He engages in a number of outreach events like this, And in fact, he was a plenary speaker in this year's European Science Open Forum, which many of you remember was actually hosted in Dublin a couple of years ago. He's an honorary member of the Royal Irish Academy, and he's also a visiting professor at UCD, so he has visited Dublin several times. Hardly probably worked as hard as he has been today, because he started off with a master class in Arab. He held a discourse with an engineer in the afternoon, followed by an award ceremony, and here he's given the lecture tonight. And I think his drawing power is recognised by the sellout crowd, and it was a sellout crowd. In fact, the lecture was delayed a couple of minutes to allow people who hadn't fully booked in. You know, they were kept out until there was a few spaces available. So it's a great pleasure to be joined by Professor Villani this evening to give his lecture entitled Thinking the Inaccessible, Large Time Behaviours from Infinitely Small to Infinitely Large to Infinitely Long. So please put your hands together to give an extremely warm welcome to Professor Villani.
Okay. Everybody hear me well? Yes, perfect. Thank you very much. It's my great pleasure to be back in Dublin again. And let's see, tonight, bring to you the inaccessible through mathematics. This is one thing that it's important to realize. Mathematics was created to solve problems, and mathematics was created to be something that helps us going beyond our intuition and the range of phenomena which we can understand and apprehend with our hands and eyes and experiments. And we'll see several examples of that tonight. Before going on to the main subject of large time behavior, let's make a few reminders of some mathematical stories enlightening us about the nature of mathematics. And let's start, why not, with the 5 great ancient mathematicians from Greece. This is one thing about technology, by the way. You know, computers improve everything. And in this particular case, the screen decided to put them a little bit slimmer than they were in reality. A little bit more elegant, you know. And we can see this. So here who do we have? Thales, Pythagoras, Euclid, Archimedes, Eratosthenes. What we know about the first 3 is essentially nothing, except some of the things they did. And in the case of Euclid, the most famous book ever written by a mathematician. One of the most famous books ever written by a human being. The most edited book in the history, set apart religious treatises, religious books. And the author of these elements that for a long time were the curriculum of all students of mathematics around the world, translated in all languages, showing that mathematics is also an art about thinking, not just solving problems, and a school of thinking. One of the most devout readers of the elements, by the way, was Abraham Lincoln, who liked to say that this is where he learned logical thinking. When I was teenager, I was fascinated by Euclidean geometry and triangle geometry. This book was one of my very favorite. You know, geometry of triangle? Yes, the computer also improves the circles, you know. You know, geometry of a triangle is based on circles, triangles, very elementary things. Let me make it clear that it has no use whatsoever nowadays. If you're a mathematician, you don't care because there is no research anymore in this field. And if you're not a mathematician, you don't care because there is no practical problem that you will solve with lines that come together or points which are aligned and so on. However, this book participated in my training as a teenager. It is through this kind of exercises that I learned how to make a proof. Later, it became my job. To get the Fields Medal, I had to put together with my collaborators proofs, some of which were more than 100 pages long about statistical physics. You know, when you have to put this together, it's good that you train before by putting together 10 lines of proof with small and easy triangles. Start with the easy, and then you go to the difficult. With geometry of triangle also you learn a very important lesson, that there are no miracles. All these miracles or the lines meeting whatever, you learn how to find the reason why. You solve the mystery, and the explanation always furnishes ample beauty to compensate for the loss of mystery. Among the 5 mathematicians I quoted, usually one considers that Archimedes was the brightest, maybe, but let's say a few words about Eratosthenes. It will also recall us some important lessons about mathematics. Eratosthenes, also a great geographer, one day used mathematics to measure the Earth. Talk of a small accomplishment. This was 200 years maybe before Christ, don't remember the exact period. And there it was, measuring the size of the Earth. How can you access this? It's so wide. Now, this was based on mathematics, not difficult mathematics. I mean, mathematics much simpler than what they were doing already 300 years before him. Just mathematics about the proportionality of the length of an arc of circle and the angle, and being clever. And he had learned that there was the sun reflecting in the bottom of a pit somewhere in Aswan at a certain precise day of the year. And anybody would have said, that's interesting. And so what? Interesting. But not Eratosthenes says, I will use this to compute the length of the Earth. How come? Well, that's the experiment. He knew that Alexandria was somehow same longitude as Aswan, and the distance between both could be measured, and the angle could be measured. How do you measure the angle? Well, if the sun reflects at the bottom of the pit, it means that that particular day it is at the vertical of Aswan. And you can measure the angle that there is at Alexandria. You just take some stick, and you compute the ratio between the length of the shadow and the length of the stick, and then you apply the basic trigonometry as we learn it in medium high school. And there it was. Extrapolate and find the length of the Earth. Converted into modern units, it is estimated to be within 2 to 3% of the actual value. Talk of an accomplishment. It is said that if Columbus 1,500 years later would have believed in Eratosthenes, he would never have mistaken the America for Asia. See this already, thinking the inaccessible. They could do it with mathematics, measuring the world in a sense. This was about measuring distances. Let's go to measuring time. Well, time, it was developed in Europe around the 13th century, 14th century, mechanical clocks. For a long time, it was believed that this was the first time mechanical clocks were made, until people discovered in some small island in Greece, near some small island in Greece, a mechanism which is more than 1,000 years older than anything that was known in terms of clocks. Nobody can explain this huge gap. Apparently at the time of Archimedes, before Christ, they were able to construct these clocks, and then the knowledge disappeared and was rediscovered in the 13th century or so. Anyway, the techniques was perfected for hundreds of years, and achieved peak maybe at the beginning of 17th century or so, with 1% accuracy, using some mechanical device regularly ticking to measure the time. 1%, it seems good, but that's not so good. It's 15 minutes per day. How do you do better? Now come the mathematicians. Okay, it's another trick of the computer, never mind. This is some pendulum, you know, like this. And working with pendulums like this and counting and measuring the length of the oscillations, at the beginning of 17th century, Galileo discovered that the oscillation of a pendulum is regular and that the time does not depend on the mass which you put in the end. It depends on the length of the string, but that's it. Oh, it also depends on the amplitude. It's not exactly the same if you do a small amplitude or a large amplitude. Okay. Later, middle of 17th century, people managed to put this into differential equations. This is the time of Newton, of Leibniz, of Huygens, and they found a differential equation, which now we learn in any course of differential equations. Acceleration of the angle is proportional to the sine of the angle of deviation. And if you look at small oscillations and make a linear approximation of the sine function, you can compute the time period that there is. It depends only on the strength of gravity and on the length of the thread. Okay, and then you say, okay, that's interesting. What next? And then come some clever mathematicians. In this case, Huygens. Huygens works on the problem of the tautochronos curve. It's the cycloid that was the solution. What is a cycloid? Cycloid is the shape that you obtain when you tag some point on the boundary of a circle and let it roll. Let's look at this animation, which I will show you from this website, cool website. See the cycloid being made? In those days, this was advanced mathematics, studying the cycloid, and the mathematicians would put up challenges based on the cycloid, compute the length, compute the area, whatever. It was a fashionable object. And Huygens discovered that the cycloid is tautochronos. This means if you put stuff, little balls, oscillating in a cycloidic well, the oscillations will be synchronized exactly, not depending on the amplitude. So some regularity property which is better than the pendulum. And this, of course, gives better accuracy. And Huygens realized this could be used to measure time. This is changing the paradigm. Before that, you were interested in studying the properties of the object as a function of time. But then you say, maybe I can study time thanks to the object. Often stories of technology and progress is like this, reverse the point of view. This is nice, but how to make a pendulum that would have this strange shape? Because the cycloid is the only curve with this. And then Huygens discovered that if you constrain your pendulum by walls which are in the shape of a cycloid, then the resulting motion will be cycloidic also. Isn't that beautiful? Look at these three pendulums. They oscillate at exactly the same period, even though the amplitudes are differing. Imagine that this is a pendulum that is swinging and loses momentum from time to time because there are some tiny change in the energy, maybe some friction. Doesn't matter. The period will always be the same, better accuracy. And in the mechanism, and Huygens had this idea to use this to make clocks really. We'll see this. Let's go back to this here. And we see this very clearly in the mechanisms from that time. You see, this is the plans for some clock from the 17th century. And you see, Fig 2 there, this is in the shape of cycloid, these two arms, and it constrains the motion to be cycloidic. And with this, there was a factor 100 in the accuracy which could be gained in the measurement of time. Now, this becomes to be serious. We're not talking about minutes which are lost per day. We're talking about seconds. And this was the start of a revolution in the way of measuring time. Then it would go again and again with knowledge of how to and so on, and culminate with the Harrison saga in the 18th century, solving the problem of longitudes, famous problem put to price by various countries at the time, which was to determine which is the longitude of a ship which is traveling. If you are on board, how do you determine where you are? It was important to prevent the ship from going through the path of some storm, to avoid wreckage, and so on. And the solution which was found to work was use the jet lag, use the difference between the local time at where you are and the time on the clock, very precise clock, which you put on board in your embarkation port. That was amazing. And the clock of Hamilton was so precise that after 3 months of sailing, the difference was only like 5 seconds compared to what it should have been. And it was another factor 100. There was a whole bit of a story, by the way, a lot of adventure with this, because the English refused to give him the money under some pretext, and he had to go to see the king directly to get the prize and so on. It's a nice story. Now, that's not the end about the measurement of time and measurement of the Earth. I told you 2 different stories, it seems. And very often in mathematics, stories are related, and we discover this later. Now, it was found by people that if you have a pendulum measuring the second, tac, 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 in Paris, if you brought it to Cayenne, you have to change the length so that it still beats the second. Not by much. If it's 1 meter long, it needs to be 1 meter and 3 millimeters long. These guys, they were amazingly precise in their experiments in those days. Amazing. I said 1 meter, but it's just proportionally, I don't know what's the exact length. This was reported to Newton. And okay, 3 millimeters more, okay. But that's not where the story ended. Newton thought about it and said, this must be an effect of the shape of the Earth not being round. And the fact, and he used the theory of gravity and computing and mathematics to conclude that the Earth had to be slightly flattened at the poles, slightly. 0.5% was his estimate. Now it's estimated the real number is closer to 0.3%. See, from time measurement, we deduce something about the shape of the Earth with amazing accuracy now. And this was confirmed, this flattening of the poles was confirmed by a French expedition of the 18th century. Again, I say it again, but see the miracle. From some tiny deviation in the length of the pendulum beating a second and some mathematics, deduce that the Earth is about 0.5% flattened at the poles. There is something miraculous in there. Also miraculous is the fact that some of the work done in pure mathematics, like theory of curvature as set up by Riemann in the middle of the 19th century, after going through the works of other mathematicians like Ricci, ends up becoming at the core of physics when Einstein discovers that it is the cornerstone of the theory of general relativity, and then goes all the way until becoming part of our daily technology when the corrections induced by general relativity and thus based on curvature computation are incorporated into GPS. Without the work of the mathematicians of the 19th century, 20th century, without the notion of curvature, without the general relativity, GPS would simply not work. And this is typical. This is typical. The things that one at first are just creations of the imagination, just curiosity, may very well end up being technology that invades the whole world and changes our habits. Let's explore another direction in which mathematics has changed our point of view about the universe, not just the scale of the Earth, but the scale of the whole solar system. In this painting by John Wright of Derby, we see a philosopher giving a lecture on the orrery. This is a mechanism reproducing the motion of the planets, in which a lamp is put in place of the sun. Of course, it lights the happy faces of the young kids, all marveled and illuminated by the joy of science. This painting was very heavily commented on because it was not some politic or heroic or religious theme, but science and science within the family, in the house. And this is a painting which still has value today, at a time in which we are in need, all of us developed countries, to motivate more and more young men and women to go into science. What can be said about the problem of describing the motion of the planets? The Greeks were fascinated by this, of course, by everything that is in the, up there in the sky. And the planets were a big problem for them because they were erratic. They call them the erratic or something like this. A star goes always in the same direction, but the planet goes sometimes like this, sometimes like this, sometimes like this. How do you reconcile this with the Greek idea that everything that's up there is perfect and has to be kind of circular? You know the reasoning. It has to be perfect, the perfect shape is the circle, so it has to be described by circle. Ptolemaios, in a wonderful work, the Almagest, one of the great astronomic works, managed to get a description of the motions of the planets using mainly circular motions, but combinations of them. The idea that if the planet does like this, and then like this, and then like this, you can construct this as a superposition of circles. It was a complicated system. Some people, by the way, say that Ptolemaios cheated completely with the observations so that it fit his theory better. He would not have been the first, if that is true. This was maybe some ancient precursor of Fourier analysis. In Fourier analysis, one has this idea that any signal, complicated as it may be considered as a superposition of elementary signals derived from circles, sines and cosines, which are projections of the circular motion. And that's a bit the same. Ptolemaios was trying to express complicated motions in terms of some simple alphabet. See this function here, I obtained it very simply by combining 4 sine functions of different amplitudes and periods and frequencies. And see, it doesn't look at all like a sine function. The moral is that, of course, if you have the motion of the planets to explain, you can always get it by putting enough circles. It doesn't tell you anything particular about those trajectories. So why prefer one description rather than the other? Well, let's go and see with Copernicus. In this famous revolutionary work, De Revolutionibus, he has an explanation which is much simpler. He still needs these funny combinations of circles, but he needs less of them. And this is achieved by putting the sun in the center of the solar system, among other things. He was not the first one to have this idea, but he deduced interesting conclusions from this, that the description of the motion is simplified. Let's continue about half a century later, and we arrive at Kepler. Kepler, mathematical descriptions of the solar system, this is a very particular moment in our representation of the solar system. This is the moment where it's purest and simplest. Before Kepler, it was complicated, like Copernicus and so on, and after Kepler, it will be complicated also. The way we think of solar system now is very complicated. But at the time of Kepler, everything seems crystal clear. Okay, in retrospect, it seems crystal clear. If you try to read the laws as explained in their Mysterium, in his Mysterium Cosmographicum, I wish you good luck. This is really esotericism. It's impossible to understand what is there. It is only after Voltaire in France translated it into language that is reasonable, that it could be taught and understood. And when you read Kepler, for instance, he explains that the planets have a friendly side and an enemy side with respect to the sun, and that the friendly side is attracted by the sun, the enemy side wants to go in the other direction, etc. It's complete mystery what he had in mind. One of the examples that shows that great scientists, many great scientists do not think logically or rationally. And it's normal. They are humans in the first place, even if the science in itself is logic. But scientists often are not. The first law of Kepler is that ellipses is the shape that a planet describes around the sun, with sun being one of the focus of the ellipse. So this is an ellipse, this is one focus, this is the other focus. The ellipse appears to you a bit more round than it should be. To draw an ellipse in your garden, it's easy. Some stick here, some stick there, and a rope, and then you stretch the rope and turn around the sticks while maintaining the rope stretched. And this is it. Of course, the ancient Greeks knew this very well, but they would never have thought that this was the solution to their problem. Just they had to change the point of view and use the sun as one of the focus of the system. Not the center, but one focus. Second law, areas are swept at uniform speed. The speed of the planet is not constant, but the areas which we swept is constant, so that here you see A has the same area as B, so it takes as much time to go from this point to this point as from this point to this point. In particular, it goes faster when it's closer to the sun. And third law, if you take the ratio of the year, the period of the planet, to the square, by the cube of what we will call the mean distance of the planet to the sun, it's some kind of mean, then you get a constant. This is remarkable, like some invisible link between all these planets, like they are all of the same nature. These are the planetary years. For instance, Mercury's year is about 1/4 of the year of the Earth, and so on. And this is the distance, in the sense of semi-major axis, from Mercury to the Sun, from Venus to the Sun, and so on. So if you square these numbers, you get the same as the cube of these numbers on the right. Telling you something that looks like a common nature of these various planets, even though they are disjoint. And with these three laws, you can describe everything. That is what we had at the time of Kepler. People tried also to explain the positions of the planets, all kinds of theories. A philosopher like Hegel, by the way, was part of the story. All of these theories failed, with the possible exception of the Bode law. And, at some point, people even tried to relate the distances of planets to the sun to the regular figures like the dodecahedron and so on, in a kind of magic way. It was not more crazy than what Kepler was thinking about the planets, but it did not work. On the other hand, so something like 90 years after Kepler, Newton publishes something that will completely change the view of the solar system, universal gravitation. Newton says, forget about the three laws, there is just one. If you have two bodies, there is a force exerted by that body to that body, and the force is proportional to the product of the masses and inversely proportional to the square of the distance. What is first remarkable is that with this one law, Newton could recover the three laws of Kepler by solving the so-called two-body problem, in which you have just the sun and one planet, and you show that the solution of this differential equation with the force is an ellipse, and so on. A second remark is that once you believe that there is such a law with the dependence on the distance, it is easy to see that it has to be the inverse of the square. Why is that so? Well, force is like acceleration. Velocity is like a distance divided by a time. Acceleration is a distance divided by the square of a time. This corresponds to units like the radius, the distance of the planet to the sun divided by the square of the period. But if we remember Kepler, this is proportional to constant divided by r squared, because r cube is like t squared. So if there is a law, it has to be this one. The great contribution of Newton is postulating that there is such a law, and that it does not depend on the fact that these are planets or whatever. It's universal. Anything which has a mass will satisfy this. Before Newton, it was supposed to be a property of planet, like maybe planet is a special object. Here there's nothing, just the mass that counts. This was brilliant in its unifying way. However, at the same time, it made things so much more complicated, because if it's property of everything, then also this planet is attracting that planet. And this will screw up the whole computation. Because if Mars is attracting the Earth and Jupiter is attracting the Earth, then this is perturbations, and the orbits will not be ellipses exactly. Actually, why would there be orbits at all? There's no reason why the trajectories would be closed. They could do anything. Maybe some catastrophe can occur, and Newton was very embarrassed by this possibility. Looking at the equations, he sees no reason why the solar system would remain stable. No reason that would prevent, for instance, Pluto to wander off in the outer space at some time, or Mars and the Earth to collide at some point. He sees no reason why this would not occur. I should add that this event was coming with the birth of infinitesimal calculus and differential equations, which have been a tremendous revolution in science and technology. And this book is another book like The Elements, which is legendary in the story of sciences. By the way, look at the words here. There is everything in the full title. Usually we say Principia Mathematica for this book, but the full title is Philosophiae Naturalis Principia Mathematica. It's about philosophy, it's about nature, it's about principles, and it's about mathematics. And that was the big work of Newton. So everybody interacts with everybody, as I said. This was a big problem with universal gravitation, and the resulting behavior can be very complex. Let me show you a little video of what may happen if we have a bunch of interacting bodies. Let's go on this one. Yes, here we go. These are stars interacting through the laws of gravitation. It will be useful for the discussion that will be at the end of my talk. And look at this. Yes, let's look at this one. Look at this. This is what you see when you let a bunch of bodies interact through the gravitation. Look at these complicated patterns and be aware that there is only one law implemented here, gravitation. Any two of these points attract each other following Newton's law. This represents basically what happens if you let a galaxy evolve for a very, very long time. It's very, very sped up, of course. Look at this beautiful thing, by the way, when two galaxies collide. It is supposed to be what will happen to our galaxy in a couple of billion years or something like that. It's very difficult to say something intelligent when you are looking at these images. Like, how should we study this? What should we look for? Which is the problem? Okay, I see this. How to find the principles that will guide us to understand what this is. Not just describing it, but understand it. And so Newton was aware, he did not have these images, but he was aware of the tremendous problems that would be caused by his theory applied to many bodies. And as soon as you have three bodies, you cannot solve the equations. This was the birth of one of the oldest and most famous problems of mathematical physics, the stability of the solar system, a problem that will run through centuries and can be used as a part of our measurement of understanding of some complex physical phenomena. Question, the solar system, which is not just any celestial system, but a particular system with a big sun and small planets. Knowing the equations, can you prove that it will remain stable for very, very, very long times? Or will it occur a catastrophe? This is the problem of stability of solar system. Now, let's make another digression about the power of mathematics to think of the very, very large. We'll embark on this discussion and discuss about what happens in a million years or billion years. That's a crazy amount of time. We cannot think of any million years. Even the best scientists have no intuition of what occurs in 1 billion years. But with the mathematics, they can do it. when you go to natural phenomena, often the distance scales also are crazy. Look at this small presentation in which we compare the size of the Earth to that of Venus. No problem. Size of the Earth, can have some intuition about it now. At the time of Eratosthenes, it was like infinity, but now we can go around it in a couple of days on a plane, even feel the jet lag in our body as a kind of measurement of the size of the Earth. And Venus appears to be the same order of magnitude. But look at Jupiter compared to the Earth. Look at the Sun compared to Jupiter. This is the Earth here, you see? This is the Sun. Look at big star like Arcturus compared to the Sun. At this scale, you can't even see the Earth. Look at Antares compared with Arcturus. That's the end, don't worry. This is the Sun. Do you see this tiny dot here at the... this is the Sun here. Why am I showing this? The moral is, these things which are crazily out of our understanding of our world, we can understand this through mathematics. For instance, we can describe with very good accuracy the motion of Antares and the motion of a galaxy, even though it's maybe at million light years away, and with scales which are crazy. And that's one of the very important things about mathematics. Now back to the solar system. Can we use mathematics to understand the fate of the solar system? As I said, solar system is not just any system. The Sun is big, and this has an impact, of course. There is an influence, true, of Jupiter on the Earth, but it has to be small. And when you look how small, it's about 1/1000th of the influence of the Sun. You may say, okay, if it's 1/1000th, it's very small effect, not so serious. If it's about 1,000, the natural guess, and that was Newton's guess, is that after 1,000 years, there should be some important influence. And the positions of the planets should be completely different after 1,000 years. This is the mathematical problem as I stated it. Just to put it into equations, let's not worry about this. Let's skip this. Just mention that other sources of errors that you can think of as very minor compared to this planet-planet interaction, except maybe the moon, which is special, and the general relativity. And let us go on with this problem. If you have a small error like epsilon, which maybe is 1/1000, after a time which is like the inverse of that small error, that should be a big problem. If your bank account loses 1 per 1,000 every day, after 1,000 days, it will not be in great shape. That's exactly the reasoning you could apply to the solar system. It took about 100 years before people could understand where the mistake was. And the mistake was in the fact that these errors, due to the influence, they usually don't accumulate in the same direction. At some point, there will be an error that will make the planet go a bit closer to the Sun, but this will be compensated by another time in which the planet will be sent a little bit further away from the Sun. And if the positions of the planets are kind of random, these effects will compensate each other to a great precision. Kind of random means that there is no correlations between the orbits of the planets, and it means that there is no such thing as, for instance, a planet that would go around the Sun exactly twice as fast as another planet. If something like this occurs exactly twice as fast or exactly 3/4 as fast as another planet, then you may have resonances, as they say, phenomena piling up. Like, you know, if you have a bridge and an army goes on the bridge at exactly the right frequency, all the perturbations will add up until the bridge can break. But if all the soldiers march at different rhythms, the perturbations will cancel out each other, and globally the bridge will stay still. It's about the same here. If there is no correlations, no synchronicity between the various planets, all the perturbations will kind of cancel out, and you will need a much longer time until some effect occurs. That longer time is like the inverse of the square of epsilon, and we are about 1 million years. And think about this. At the end of the 18th century, the mathematicians, especially in the French school of the time, Lagrange and Laplace, they had understood that for 1 million years, the solar system would remain essentially like it is. This is extraordinary achievement, if you think about it. Let's continue this. Yes, they also, by the way, look just at this thing, noticed and confirmed that with the single Newton law, you could explain all astronomic phenomena recorded to that day. Just one law for all the phenomena of the universe. The Greeks would have died for this. You see that we already changed point of view several times, from Ptolemaios to Copernicus, to Kepler, to Newton, to Lagrange. Now we'll change for the 5th time of point of view on this problem with Poincaré in France at the end of the 19th century. Poincaré studies the restricted free body problem. This means let's simplify things and make this abstract. Just consider the Sun and say Jupiter, and the Earth, and consider that the Earth has a mass so small that it will not affect the position, the motion of Jupiter. It's called restricted three-body problem. 2 big bodies and one very, very small, which doesn't influence the other ones. It's the simplest you can imagine, which is not exactly solvable. And Poincaré asks, okay, it's stable for a very long time, but will it be stable forever? As a baby problem of understanding whether the solar system will be stable not for 1 million years, but for 1 billion years, or even longer. And Poincaré believes he can solve it, and in what is one of the most dramatic events in the history of sciences of 19th century, Poincaré wins this famous competition that was set up by King Oscar of Sweden at the time, together with mathematician Mittag Leffler on the left. So Poincaré manages to prove, using revolutionary techniques, that basically it is always stable. And that if you look at this restricted three-body problem, in very, very large times, it's the same whether you go to the very large positive times or the very large negative times, very far in the past or very far in the future. Wins the big prize, becomes famous, is all in the newspapers, and so on. Okay, and then it was part of the prize that he be published in Acta Mathematica, the leading mathematical journal of the time. And it was known to be quite something to publish Poincaré, because the style was horrible, little mistakes everywhere, you have to correct everything and so on. And so the mathematician who was in charge of this sends many remarks to Poincaré, and Poincaré answers everything. But then one day Poincaré realizes, gosh, it's all false. It's all false. So there was a fatal error, that's how we would say it at some point. Stupid errors. Think something, dimension 2, dimension 3, whatever. And realizes that at some point it's much more subtle than he believed. And there is a certain curve. He thought the 2 curves were the same. In fact, they intersect each other infinitely many times, but they are not the same, and it's a big surprise for him. Little problem. The paper is already published, and he's very famous, and they all talk about the brilliant work and so on. What to do? Okay, Mittag Leffler, who was the editor, did not lose his temper, managed to get back all the copies of the journal. Please send me back. There is a small problem here. I will send you back a new one, a Polish. Destroys them all, except 3 that he keeps for the record. They are still in Institute Mittag Leffler in Sweden as a testimony. Has Poincaré pay for this, which cost Poincaré more than the money of the prize. There's a moral to the story. And Poincaré can think again. Now, the amazing thing is that Poincaré manages to resolve the problem. And there it is. He gets it. Repairs all the proofs and so on, and finally has this beautiful proof, very brand new and so on. Just one small thing, the conclusion was the opposite of the previous one. He thought it was stability, and in the end it is unstable. And Poincaré here discovers this phenomenon called homoclinic intersection, which is now well known as an effect for chaos in a system that can bring in the instability in the solar system. And this is a big mistake, but a very fruitful one. And Poincaré discovers that there is this beautiful thing here. Let us try to represent the picture formed by these two curves and their intersections with infinite number, each of which corresponds to a solution doubly asymptotic. Doubly asymptotic solution, let's say it's a stable solution. He wants to find where the stability is, and there are two curves in the mathematical problem. Intersection corresponds to stability. And it forms these intersections are arranged according to some kind of mesh, of tissue, of fabric, of network, with the infinitely close to each other. Each of these curves must never intersect itself, but has to fold itself in a very complex manner to intersect infinitely many times every mesh of the network. This is so complicated I don't even try to draw it. Computers nowadays draw it. This was the start of the theory of dynamical systems, and Poincaré is considered the founder of modern theory of dynamical systems. If you followed the mathematical activity recently among the last round of Fields medalists, Arthur Avila, French-Brazilian mathematician, was awarded Fields Medal last August, and he's a specialist of that theory of dynamical systems, and in this sense, a mathematical heir of Henri Poincaré. And from this, we discover chaos seems to be the general rule. From the work of Poincaré, people believe that if you make any tiny change in the motion of the planets, this will change the stability conclusion in a dramatic way after the right amount of number of millions of years. Chaos theory will go its way. It will be found again in some problems of meteorology, still debated to this way, what is chaotic, what is not. In popular say is about the butterfly effect, which is the way to talk about that theory of instability discovered by Poincaré. And that was not the end of the story. 1954, new change of point of view on this with Kolmogorov. Kolmogorov states a theorem of considerable influence. This is the beginning of Kolmogorov-Arnold-Moser theory. If you perturb a completely integrable system and choose an initial configuration randomly, then with high probability you stay on a confined trajectory. So Kolmogorov says, okay, instability is possible, as Poincaré showed, but I see that it is unlikely. And with high probability, say 99%, it should be stable. This was revolutionary. By the way, here, I put the words completely integrable. There is a technical word I did not put here to simplify, but I should have put the technical word here is Hamiltonian. Kolmogorov-Arnold-Moser is a theory of Hamiltonian perturbed systems. Hamilton would never have dreamed about such a theory, but it was the genius of Hamilton to discover the right structure that would later make its way as a great general fundamental structure in which you can put many, many different theorems and effects. And the solar system is a Hamiltonian system among many others. Okay, the Kolmogorov-Arnold-Moser theorem is a beautiful theorem. Can you apply it? No. The planets are too big. It's a beautiful theorem, but in practice you can never apply it. What's it good for then? Answer it, it changed our vision of the world. Sometimes theorems are good because you want to apply them or make a new device, technology, whatever. Sometimes it's good because it changes your point of view and you realize some effects are important which you had not seen. The theorem is like the revelator of something. And this Kolmogorov theorem will change the way we see the stability problem. Also, it was the start of an important, elegant, active mathematical field with far-reaching applications for many problems outside the solar system problem. You know, in mathematics, it's like imagine you are making this big hammer to solve the problem. But sometimes the hammer is more important than the thing you're trying to solve because you can reuse it in many other problems, and that's the case here. Okay. So many changes of point of view already on one same problem. But that's not the end. Okay, let's skip the digression about random number. In the 80s, arrived the computers, and then Lascar, Tremaine, and others ran the race for numerical simulation over tens of millions of years. First for asteroids, then for the whole system. And what do they discover? It was a change of point of view because in those days, people believed that even though the Kolmogorov theorem does not apply, it gives the right answer and the solar system is stable. And what do they see on their computer? Instability. Instability, very much like Poincaré had guessed. In this kind of problem, the choice of numerical methods is crucial. If you just ask your computer to solve the Newton equations for 12 millions of years, 100 millions of years, I mean in the time of the computation, you are most likely going to end up in things that make no sense. You really have to be very accurate about the method which you use and think a lot. If you listen to talks by these people, they would spend maybe 1/3 of the talk explaining how they do the approximations and which is the numerical method and so on. Don't think that the computer is something you just feed the equation and gives you a result. You have to think very carefully the way the computation have to be done for such a tricky thing. Jacques Lascar writes down a simplified perturbation system of 150,000 terms, polynomial of degree 5 in 16 variables. This is a simplified thing, describing the evolution of Keplerian orbits. Again, one has to think really why such a monster thing would be a simplification compared to the single equation of Newton. And the answer lies in the behavior with respect to long time, with respect to the errors and so forth. And what they discover is this instability and growing of errors. Look at this beautiful formula, which Lascar considers is very close to the reality in solar system. If you take two small objects that you put in the solar system close to each other at some random place, typically the distance between both, the error will increase exponentially fast, and the coefficient is like 10 to the t over 10, where t is time expressed in million years. So if you make an initial error of 15 meters, for instance, for the position of the Earth in your equations, after 10 million years, maybe this error is like 150 meters, nothing. But if you wait for 100 million years, this means, wow, you see, 150 millions of kilometers. Do I get it right in number? This is kilometers? Yes. This is about the distance of the Earth to the Sun. And so your error becomes monster after 100 billion years. This is the conclusion of Lascar and the others. It's okay for predicting the evolution of the planets after 10 million years, but not after 100 million years. And there is nothing that can predict the evolutions after 100 million years because it would depend on such tiny precision and errors that you cannot do it. This is not the end of the story because they say, but we can do it probabilistically and compute the probability that the solar system will be stable or unstable. Current belief, according to Lascar, about 1% chance that planets get lost or hit each other before the end of the solar system. He thinks also that such an event probably occurred before. Let us watch a small video that Lascar himself made to summarize these findings. Due to planetary perturbations, the orbits precess and are deformed. These are the orbits at each instant, and you see Mars is in red, the Earth in blue, and so on. The orbits are almost in the same plane. They were all formed together, you know, these planets in the solar system. Nothing particular happens in the first hundreds of million years. But you see, this is not good. After several billions of years, there is a small chance, after billions of years, that chaotic diffusion, so due to chaos it changes a little bit, destabilizes the orbits of Mercury, Mars, Venus, and the Earth. Collisions become possible between Mercury and Venus, Mars and the Earth. Yeah, not good, I tell you. And even Venus and the Earth, the twin sisters of the solar system. Mars may hit the Earth. Well, this is an artist's view. By the way, what is impossible in this view? What do you think?
Configuration of the continents.
Absolutely. One bonus for you. So, it's, of course, in 1 billion years, the continents will look nothing like what they look nowadays. But then we would not have recognized the Earth, probably. Okay. See how beautiful? There's only 1% chance he thinks, okay, well. Okay, let's use a few more minutes first to comment once again on the fact that in this there is a progress in the understanding of this problem, but also the fact that many techniques were developed for this problem which were then used for various purposes. To quote just one example, which is even beyond this list, matrix, which we all use, matrix analysis, was developed by Lagrange as a way to understand the stability of solar system, because if you want to solve the differential equations, the linearized differential equations, you need some matrix calculus to do this, and so forth. Okay. Imagine now you don't care of the solar system because you want the bigger picture and think about the stability of a galaxy. Galaxy is something like 100 to 1,000 of billions of stars. Did you see how complicated it was with just 9 planets and 1 sun? What will it be with thousands of billions of stars? The answer is that it is not more complicated, provided that you look at it from the right perspective. And the key word is statistics. You see, if you take a coin, throw it in the air, and try to predict which will be the outcome, it's very difficult. But if you throw a coin in the air 1 million times and try to predict the outcome, it is very easy, provided you look at it statistically. You know that about half of the time it will be head, half of the time it will be tails. And that's about the same thing with the galaxy. The fact that you have many, many, many stars will help you if you are looking at it from probabilistic perspective, not be a nuisance. So it came out from the works of the pioneers of statistical physics, Maxwell, Boltzmann in the 19th century, Vlasov in the 20th, that you can use statistics to describe the behavior of a gas. This was a revolution, by the way, in the terms of Maxwell and Boltzmann. Think, replacing the idea of the air around us, which looks like still, by a chaotic vision in which molecules go in all kinds of directions, hit each other, hit us, and so on. If I, knowing nothing about physics, wanted to attribute a mathematical value to the air around us at this moment, the natural outcome would be 0. There is nothing going around us, 0 velocity. And they replaced this by a vision in which it's in fact numbers, all kinds of numbers, velocities going in all directions and changing at each instant of time in a crazy way. It looks amazing. And this was the scientific revolution. In this new formalism, the unknown is not the positions and velocities of the molecules, but the statistical distribution, which is the proportion of fast molecules, which is the proportion of slow molecules, and so on. And similarly, if you look at a galaxy, you know, at the scale of a galaxy, a star is like a molecule, almost. It's so tiny. And you can make this statistical description of the galaxy in which our sun would be just one individual among many, many, and you are asking how many, which is the proportion of stars which are slow, proportion of stars which are fast, proportion of stars going this direction, proportion of stars all crammed into this small space, and so on. So statistical distribution in the space of positions and velocities of the stars. And now you need an equation. Okay, we know the Newton equations, but we don't care about the positions, I told you. We care about the statistics. So we need an equation on the statistics. This is where the Boltzmann equation comes in the game. It's still very mysterious today, even though we understand it much better than Boltzmann. This would be an evolution equation for the statistics, allowing to predict the evolution of the statistics in time. To take an analogy with things we know better, think about demography. It's impossible when you talk about an individual to predict if that guy will have children, will marry here, there, what if he will go abroad, whatever. But people in demography, they can very well predict what will be the population of a country 10 years from now, taking into account the rate of immigration, the rate of death, the rate of birth, and so on. With these big quantities, they can predict statistically what will occur. And the same for molecules. We are unable to know if this molecule will be here or there or down in the corner after a few seconds. But we can predict for sure what will be the density of particles in that corner and so on, and the Boltzmann equation will give it to us. Boltzmann made this amazing discovery that if you take this equation, spontaneously the entropy, which is a measure of disorder, increases, so that the galaxy would go toward a state which is as disordered as is possible. And this forces the approach of very special statistics, Gaussian statistics. This is a prediction made by Boltzmann. So take a galaxy, wait for long enough, the velocities will become Gaussian. Isn't that some answer to our stability problem? Looks like it. However, in the 60s, it was pointed out by astrophysicists that even if it's true that there is a tendency to relaxation of galaxies, which often appear to be in some kind of equilibrium, it's not due to entropy. If we compute the time scales needed for the Boltzmann equation to operate, it will be totally unrealistic. You would need thousands of billions of years before this effect takes over. So it has to be another explanation, not based on the Boltzmann equation. They call this in the astrophysics world violent relaxation. It's a nice oxymoron now, violent relaxation. If you ask them what it means, they will say that they have no idea, but it has to be something that makes it relax, that makes it equilibrate without any increase of disorder. Okay. Then they will ask, maybe some mathematician can explain this, and say, okay, we'll try. And this is still one of the big mysteries in this. People agree to say it's important and it's true, but how to prove it? Lynden-Bell argues using the so-called Landau damping, which you were mentioning at the beginning because I worked on it. This is a picture of Lev Landau. He does not look happy. This is normal. It's a picture of the time where he was sent to prison for no good reason except being Jewish, among other things, by the Soviet government at that time. And he was out of prison then, thanks in particular to the solidarity of his colleagues, and continued his amazing work. And 1946 argued about this Landau damping, that if you take the Vlasov-Poisson equation describing a plasma, this is not the Boltzmann equation. The Boltzmann equation takes into account collisions between particles. Here there are no collisions in the Vlasov-Poisson equation, and the entropy remains constant, not increasing, constant. Then there should be dynamical stability of homogeneous equilibria. Wow, what does it mean? It means you start from a statistical distribution which is in equilibrium at rest, and same profile in each point of the plasma, velocity distribution. Perturb it a little bit, maybe with some electric field, then spontaneously the electric field will disappear and there will be again equilibration. This was Landau's contribution. And he gives some hints for that, makes the linear analysis to show that it has to be. It's tricky. And he does this using the Vlasov equation. You see, plasma, you can think of it with all these beautiful phenomena, as you find them on online encyclopedias. But you can also think of it with this beautiful equation, which is the Vlasov equation describing the plasma dynamics. And Landau started from the equation, goes to an approximate equation called linearized equation, and using it argues that it has to be this damping phenomena. And then Lynden-Bell, 20 years later, says in the galaxies, it has to be the same as in the plasma. There should be a phenomenon analogous to what Landau found, which makes the galaxy go to rest faster than what is due to entropy. Okay. Why not? Does this Landau damping really hold in very large time, also for gravitational interaction? It's tricky to answer. Why is he allowed to linearize? Is there not a problem there, a logical problem? If you think about it, there seems to be a big problem for various reasons, which I won't detail, but it seems like there is a logical problem in Landau approach. And so this was some kind of controversy for some time among the mathematicians. And physicists were giving differing answers with respect to this. We solved this problem together with my former student Clément Mouot around 2009, proving, based on the mathematical equation, the nonlinear one, that the Landau damping does hold for perturbations of homogeneous equilibria for nonlinear gravitational Vlasov-Poisson model. So, solving part of the debate with the mathematical theorem. More important than solving the theorem was the new tools. In particular, we showed new insights into this, and that there is a close link between this phenomenon of Landau damping and two of the most famous paradoxical phenomena of theoretical mechanics of the 20th century. One is the Kolmogorov theorem, which I already mentioned, and the other one is the plasma echo. What is the plasma echo? Well, this experiment, discovered in the 60s, take a plasma, which is basically a gas in which electrons have been separated from the nuclei. So you have this soup of electrons. Take a plasma at rest, no electric field caused by the electrons. Apply a small electrical impulse. Wait for the plasma to calm down. Apply another electrical impulse after some time at some different frequency. Wait for the plasma to relax. And you will see the spontaneous response called an echo occurring after you've made this second impulse. Just once. This is called the echo. And it shows that plasma is a weird thing and that plasma reacts with delay and so on. What we found is that this delay is key in the stability problem. The delay comes with some stabilization, and it was going through some very subtle analysis of the nonlinear effect going in the plasma. In conclusion, this was just one ingredient among a number of them. The proof was long. By far, this is the longest proof on which I have ever worked. More important than the solution, it was introducing new ideas and new points of view, and ending up a theoretical controversy going for quite some time. Once again, the result is important, but the tools and the ideas are more important. If I try to explain what provokes the relaxation, a good analogy is like when you are watching at an ant's nest. You know the ants going in all directions? If you try to follow the direction of one ant, you may see that it is less erratic often than you would think. If there is meeting of two ants, there will some interaction, but then they will continue their road often, as if they don't know each other. So, with this in mind, it seems that there would be no kind of relaxation. Ant goes this way and does not have some equilibrium behavior. But if you look at the whole thing, with all the ends going in various directions, various speed, it may look like it's something at equilibrium because of all the averaging over all these possibilities. It's this mixing phenomenon which is key to the Landau damping. Stated like this, it looks like fun. But it's also a 180 page long paper with that kind of thing in which, of course, you cannot use the ant to convince your reader, but you have to go through the tricky mathematics. It's also part of the game. And I wanted to insist on these two. Mathematics is three things at the same time. It's a science trying to answer questions and build knowledge. It's a social activity with the interaction of people and scientists. It's also an art in itself. And the architecture of the proofs, the techniques you use, the style, the elegance of some solution, the way the computations are made and so on, all this contributes to the style and to the art. And that will be the conclusion for tonight. Thank you.
Oh, he's great, really. He's fantastic. He's as well as being an intelligent man and a fantastic mathematician, he's really good at conveying his ideas and just his work in a way that's kind of not very common, really. But no, he's really fantastic.
I found the lecture thoroughly entertaining, amazingly lucid for me. I'm not a mathematician. I have come as somebody who's not just amateur, but really outside the field. And in spite of that, I found myself carried along, enthralled by the story he was unfolding and the logic, which was understandable to a total outsider. So I have never had an experience of such a lecture, and I think it's brilliant.
Oh, I'm thrilled. Absolutely gaga. And I might say I'm a 77-year-old physicist and slightly a mathematician and a computer scientist, so naturally I'd be very enthused.
Well, I thought it was amazing. I like to study the world of mathematics. I'm so impressed by this guy. Like, he's an amazing mathematician, and I think it's a good way to encourage students, as we're students, in that way, when studying mathematics. And I'm French, so it's French as well, and I'm from the same town as this from. So it's kind of a great coincidence.
I think he's a great lecturer, delivers his material very, very well. I did not understand some things, I'm only in second year, but it was still very interesting, and I'm looking forward to studying it now.
Almost every question he had a very unusual lateral thinking way of coming at a solution. I think that's probably the gift of the really deep thinking mathematician.